Hello, and welcome to the session on algebraic proofs. The three things that we are going to learn in this lesson are, we'll first understand what do we understand by algebraic proofs. Then we'll understand how do we represent some specific category of numbers algebraically. And finally, we'll understand how do we use those representations, algebraic representations, to prove some relationships, okay, algebraically. Let's get started then. What are algebraic proofs? Well, to prove a mathematical relationship using the rules of algebra and without using any specific numbers as example, which means in these proofs, you cannot use numbers, okay, as examples. We need to prove it algebra to prove it as a general case. Let me give you an example, okay. Prove that the sum of an even number and an odd number is always odd. Now we all know we can use some random examples like 2 plus 3, an even plus an odd gives you 5, which is an odd. 4 plus 7, even plus odd gives you 11, which is again an odd. 8 plus 5, even plus odd gives you 13, which is an odd. So we can prove using these specific numbers that even plus odd is odd. But what if this is true only for these specific examples? How do we generalize it? How do we know that it is true for every number in this world? What if there are a set of even and odd numbers which add to an even number and we are not sure about them, right? So in such cases, we need to prove them algebraically so that it's true generally. Okay, it's not true for some specific set of numbers, it's true in general. So these are called algebraic proofs. When we prove a particular mathematical relationship using algebra, okay, that's when we say these are algebraic proofs. To prove any mathematical relationship algebraically, we need to be understanding, okay, how do we represent specific numbers algebraically, right? So let's first understand that. How do we represent an even number algebraically? So examples of even number are 4, 8, 14, 20. Now, what is important in an even number? In an even number, the important thing is it always has a factor 2 in it, right? And hence, an even number can be represented as a 2n. That's the general way in which you can represent an even number. What about an odd number? Okay, examples are 1, 7, 11, 21. Now remember, odd number is always one more than an even number, and hence it doesn't have a factor 2 in it, correct? So we can represent an odd number as 2n plus 1. How do we represent two consecutive even numbers? Okay, let's take an example. 6 and 8 are two consecutive even numbers. So what is the necessary thing for two consecutive even numbers? In case of two consecutive even numbers, they will always have a difference of 2, which means the bigger number will always be 2 more than the smaller number, right? So if one of the numbers is 2n, because they are even number, remember? So one of the numbers is 2n, the other one has to be 2n plus 2. How about two consecutive odd numbers? Okay, once again, if you take an example, 7 and 9, the difference between two consecutive odd numbers also has to be 2. So if the first odd number is 2n plus 1, that's how we represent an odd number, remember? The next odd number, because it is consecutive, it will be 2 more. So 2n plus 1 plus 2 would give you 2n plus 3. So two consecutive odd numbers can be written as 2n plus 1 and 2n plus 3. What about two different even numbers? Okay, because they are not linked by any rule, okay, we cannot, because they are not consecutive. So we cannot comment on what could be the difference between them. But all I can say is the factor 2 has to be common to both the numbers because they are two even numbers, right? So if one of them is 2n, the other might be 2m, right? Because all I can say is 2 has to be a common factor between both of them, but I cannot link both of them by a rule. Like in previous case, we knew that the difference between two consecutive even numbers was 2. In this case, we can't say that, right? So we just randomly assign two different letters. One of them is 2n, the other one is 2m. Likewise, in case of two different odd numbers, like a 5 and 11, if one of them is 2n plus 1, the other one will be 2m plus 1. Two different letters again, right? Having understood this, you should be able to do these now. How do you think you can represent a multiple of 3? In a multiple of 3, the only factor which is common is 3, right? 3 is common to all multiples of 3. So we can represent multiple of 3 as 3n. Two different multiples of 3, one of them is 3m, the other one is 3n. Two consecutive multiples of 3. What's special about two consecutive multiples of 3? The difference will always be 3, right? Like 5 and 8, 7 and 10. No, sorry. These are not multiples of 3. Multiples of 3 would be 6 and 9, right? Difference of 3. 12 and 15, difference of 3, right? So if one of them is 3n, the other one would be 3n plus 3. A square number, that's easy, right? A square number can generally be represented as n squared. Different square numbers, n squared and m squared. Consecutive square number. Now this is interesting. So if one of them is n squared, the next square number will be the square of the next number from n, right? So n squared and n plus 1 the whole square. Please understand this carefully. So if one square number is 4 squared, the next square number has to be 5 squared, right? So if one of them is n squared, the next square number would be n plus 1 the whole square, right? So you should be in a position to represent these numbers algebraically, as only after this will you be able to prove mathematical relationships algebraically. Let's take examples. Prove algebraically that the sum of two consecutive numbers is odd. So any two consecutive numbers in general is odd. So if I take the first number as n, the next number will be one more because it is consecutive, right? So next number will be n plus 1. What happens if I add? Because we are given sum, right? Sum is add. Well, as you can see, n plus n is 2n plus 1. So you're left with 2n plus 1. And if you look at it carefully, 2n is an even number. It's a multiple of 2, right? Plus 1 will make it odd. So hence we have proved that two consecutive numbers when added gives you an odd result. Simple as that. Prove algebraically that the sum of two even numbers is even, right? Are they talking about two consecutive even numbers? No. Generally two even numbers. So if one of them is 2m, the other will be 2n. You know that, right? And if I add them, because they're unlike, all I can do is take two common, and in the brackets we can have n plus m, right? 2n plus 2m can be written as 2 brackets n plus m, which in itself is a multiple of 2 because it's multiplied by 2, right? 2 times a number, which means that is an even number. So we have proved that sum of two even numbers is even. Okay, prove algebraically that the sum of two odd numbers is also even. Can you? As you can see, one odd number is 2n plus 1. The other one would be 2m plus 1. There's no relationship between the two odd numbers. So we change the letters. That's it. If I add them, what will you get? 2n plus 2m will actually be 2n plus 2m because they are unlike terms. We cannot add them. And 1 plus 1 is 2, right? Now, what is common to all the three terms of this expression? It's 2. So we can take 2 common. And in the brackets, we'll have n plus m plus 1. Now this clearly is a multiple of 2 because it's 2 times some quantity. And hence, it is an even number. So we proved that sum of two odd numbers is even. Okay, let's take some more easy examples. Prove algebraically that the sum of an even number and an odd number is odd. Let's take even number as 2n. An odd number as 2m plus 1. Okay, there cannot be any link between the two. So I change the letters as well. So one of them is 2n because that's even. The other one is 2m plus 1 because that's odd. What happens if I add them? Well, 2n plus 2m goes as it is, and plus 1 is left as it is, right? 2n plus 2m plus 1. But what's common to the first two terms of this expression? The factor 2, correct? So I can always take 2 common from the first two terms we'll be left with n plus m, 2 brackets n plus m, and the plus 1 will be left as it is. Now, if you look carefully, this is a multiple of 2 plus 1, right? 2 times something, which is an even number because it's a multiple of 2, plus 1 makes it an odd number, right? So we have proved that a sum of an even number and an odd number is odd. Let's go to the next one. Prove algebraically that the difference of an even number and an odd number is odd. Okay, so let's take even number as 2n and odd number as 2m plus 1. The difference is minus, right? If I expand that, I'll get 2n minus 2m minus 1, right? Because if I expand the brackets, the minus applies to both the terms inside the bracket, correct? So it will minus 2m minus 1. In the first two terms, the factor 2 is common. So if I take 2 common, I'll be left with n minus m, and the minus 1 has to be left as it is. What can you say about this expression? Is it even or odd? The first part is even because it's 2 times something, right? 2 times something is even. But the moment I make minus 1, even minus 1, which means we have a number which is 1 less than an even number, which is an odd number, correct? So we have proved that difference between even and odd number is odd. Prove algebraically the difference between two odd numbers is even. Okay, so let's take two odd numbers, 2n plus 1, and the second number is 2m plus 1. And the difference means you need to take away. Once again, the minus sign applies to both the terms inside the brackets. So we can simplify that as 2n plus 1 minus 2m minus 1. As you can see, the plus 1 and the minus 1 cancels. So you are left with 2n minus 2m. If I take 2 common, I'll be left with 2 brackets n minus m. That clearly is an even number because it's 2 multiplied by a number, right? 2 times something, which is an even number. So we have proved algebraically that the difference between two odd numbers is even, right? So we have started with some easy proofs, okay, which involve even and odd numbers. Now let's go on to some difficult ones. Prove that the sum of three consecutive even numbers is always a multiple of 6. Now, the important word here is consecutive. Remember what is special about consecutive even numbers? The difference will always be 2, correct? So if the first even number is 2n, the next one will be 2n plus 2, and the third one will be 2n plus 4. Because remember, every subsequent even number will be 2 more than the previous even number, right? If I add all of them together, I'll be given 2n plus 2n plus 2 plus 2n plus 4. 2n plus 2n plus 2n is 6n. 2 plus 4 is 6. So 6n plus 6. What's common between the two terms here? 6, right? So it's 6 times brackets n plus 1. Clearly, because it is 6 times something, it has to be a multiple of 6. So we have proved that sum of three consecutive even numbers is always a multiple of 6. Prove algebraically that the product of two odd numbers is odd. How do we represent odd numbers? 2n plus 1, and the other one, because there's no link to the first, it will be 2m plus 1. Correct? Product. Now that's multiplication. Now, do you know how to multiply brackets with two terms? Well, the simplest one is the grid method. You must have learned the grid method, wherein we put the two terms of first bracket on the columns and the two terms of the second bracket along the rows. And when we multiply each row with each column, okay, so each cell. So 2n times 2m is 4mn. 2m times plus 1 is 2m. Okay, then we multiply the first column with the second row. 2n times plus 1 is 2n. And 1 times 1 is 1. I'm sure you are familiar with this method, right? The grid method of multiplying brackets containing two terms. Well, if I put all of them together, I'll be getting 4mn plus 2m plus 2n plus 1. Now, is there anything common which I can pick up from all of them? Not really. But from the first three terms, I can clearly see that 2 is a common factor, right? 4, 2, and 2. 2 is a common factor. right? If I put that 2 common in the first 3 terms, I'll get 2 times brackets 2mn plus m plus n. And then outside the bracket, we have a plus 1. What does that mean? This is 2 times a number plus 1. 2 times a number makes it even number, plus 1 makes it odd number. So that's an odd number. So we have algebraically proved that the product of 2 odd numbers is odd. Okay. Prove algebraically that the square of an odd number is odd. Well, 2n plus 1 the whole squared. Odd number is 2n plus 1. Square of it is 2n plus 1 the whole squared. Now, how do we square this? It's like multiplying 2n plus 1 by 2n plus 1, right? So we'll use the grid method once again. 2n plus 1 along the columns and 2n plus 1 along the rows. Let's see whether we'll be able to do the required proof. What is 2n times 2n? It is 4n squared. 2n times 1 is 2n. 2n times the other one is 2n. And 1 times 1 is 1. If I put all of them together, I should get 4n squared plus 4n. Remember, 2n plus 2n is 4n plus 1. Can I take anything common in this? From the first 2 terms, I can take 4 common, right? So we can have 4 brackets n squared plus n, and the plus 1 goes outside the bracket. Clearly, this is an odd number again, because the first part is 4 times something, which is an even number. 4 times a number is even number. Plus 1 makes it an odd number, right? So you have proved algebraically that the square of an odd number is odd. Prove that the sum of 2 consecutive square numbers is an odd number. And that's interesting. Let's take first square number as n squared and the second square number as n plus 1 the whole squared. Remember, if I have 2 consecutive odd numbers, if one of them is a square of n, the next odd square number should be the square of n plus 1, right? Now the first one is n squared. I can simplify that clearly. Let's simplify n plus 1 squared using the grid method. So we have n and plus 1 along the columns, n and plus 1 along the rows. What's n times n? That's n squared. What's n times plus 1? That's n. N times the other plus 1, n. And 1 times 1 is 1. If I put all of them together, I'll get n plus 1 the whole square as n squared plus 2n plus 1. And we already had an n squared earlier, right? So together, if I put them, I get 2n squared. Remember, n squared plus n squared is 2n squared plus 2n plus 1. What can I take common out of this? From the first 2 terms, I can take 2 common. So I'll be left with 2 brackets n squared plus n plus 1. Now, if you look at it, 2 times a number, which is even number, plus 1 makes it an odd number. So that's an odd number. So we have proved that the sum of 2 consecutive square numbers is an odd number. Prove that the difference between the squares of 2 consecutive integers is always equal to sum of 2 consecutive integers. Now this is interesting. Difference between the squares of 2 consecutive integers. So first, let's pick 2 consecutive integers, square them. So if one of them is n squared, the other one would be n plus 1 squared. Remember, these are consecutive integers. So they are next to each other. The second number has to be 1 more than the previous number. And then we square each of those integers. So if one of them is n squared, the other one will be n plus 1 the whole square, right? And we need to find the difference between them. Read the statement. Difference between the squares of 2 consecutive integers, right? How do you find n plus 1 the whole squared? Using the grid method, you'll realize that that's n squared plus 2n plus 1 minus n squared. So the n squared and n squared gets cancelled and you're left with 2n plus 1. Now what do we need to prove? We need to prove that this difference of the squares of 2 consecutive integers is always equal to the sum of 2 consecutive integers. Now is 2n plus 1 sum of 2 consecutive integers? For that, we need to split 2n plus 1 as n plus n plus 1. Now, as you can see, n and n plus 1 are consecutive integers, right? Because 1 is one more than the previous one. So this is sum of two consecutive integers. And hence, as you can see, we have proved that the difference between the squares of two consecutive integers is actually equal to the sum of two consecutive integers, right? So these were some of the ways in which you could prove a lot of mathematical relationships algebraically, right? And you can now generalize it for any other relationship, right? You would have understood that. So the three things that we learned was, first, we understood what are algebraic proofs, okay? These are proofs which are constructed using rules of algebra and not really using some numbers as specific examples. Then we understood how do you represent certain numbers algebraically, like an even number, odd number, square number, consecutive even, right? And so on. And finally, we used those representations, okay, the number representations which we did algebraically to prove various mathematical relationships. I hope you understood the concept which was taught in this lesson. Thank you.